Hello friends. So as I have explained you the aim, apparatus, then theory and procedure for the experiment, like determination of free chlorine from the given water sample. Determination of free chlorine from the given water sample, and the type of titration involved in this experiment is iodometry. So it is also called as iodometrical. So everything is explained to you now. Now directly I will demonstrate you the part 1 of this experiment as standardization of Na2H2O3 solution. So in this experiment you have to standardize this solution because it is not a standard solution. So to standardize this solution is used like K2Cr2O7 and its normality is given to you, that is N by 100. So using this solution we are going to standardize now Na2H2O3 solution. Okay, so let us see the demonstration of the first part of the experiment, that is standardization of Na2H2O3. So what are the solutions required now? So as per the experiment we required now the K2Cr2O7 solution. So this yellow colored solution is a K2Cr2O7 solution whose normality is given to you, that is N by 100. Then we require this Ki solution, that is potassium iodide solution. Then we require a SCl solution, SCl. Then we require a starch solution. So in this experiment the starch is used as an indicator. So see the procedure. First you take pipette out 10 ml of this K2Cr2O7 solution like this and adjust to 0 like this. Release the solution slowly and adjust to 0. Take the lower meniscus. In this way you transfer this solution to this conical flask. So this is a 10 ml of this K2Cr2O7 solution. Then add a concentrated HCl 5 to 7 ml. Means you add this amount of solution 3 times like this approximately. This is nearly equal to 5 to 7 ml. Right. So in this way add HCl solution and then add this half test tube of Ki, freshly prepared Ki solution. Freshly prepared Ki solution. And then see, we have added now, we have taken 3 chemicals in the conical flask like 10 ml K2Cr2O7, then 5 to 6 7 ml HCl and half test tube of potassium iodide. Then immediately you stopper this conical flask like this with the help of rubber and wait for 2 to 3 minutes for the liberation of iodine in the conical flask. So there is a liberation of iodine, and that I have already explained to you in the theory part, that how this iodine is generated in the conical flask. So wait for 2 to 3 minutes. And during this time now, you fill your burette, this burette with a Na2H2O3 solution. Na2H2O3 solution means a sodium thiosulfate solution. So just you add this solution in a burette like this. And if there is air bubble, see, if there is air bubble, you remove this solution fastly now and remove this air bubble like this. The solution should be continuous now in the burette. And then after removing this air bubble, again add this solution Na2H2O3 solution and adjust to 0. Adjust to 0. So exactly take the lower meniscus, that is. So we have added this Na2H2O3 solution in the burette now. So this is ready for titration now, and after 2-3 minutes, 2 minutes like this, see there is a generation of iodine. There is a generation of iodine in the conical flask. So in this way, after 2-3 minutes, you remove this conical flask, okay, and go on titrating this solution against this solution, that is Na2H2O3 solution, and make it faint yellow. Make it faint yellow. See, the original color was dark brown. Now we have added Na2H2O3 to this solution, and therefore this iodine gets consumed now, and therefore the color of this solution becomes faint. So just you titrate till you get faint yellow color. Till you get faint yellow color. Now this is faint yellow color, and at this moment, now you add the freshly prepared starch solution with the help of directly bottle like this. So remaining iodine reacts with starch and it gives I2 starch blue colored complex. So this is a blue colored complex, and our aim is to titrate this solution continuously again Na2H2O3 till this color disappears. Means when iodine concentration becomes 0 now, that I2 starch complex breaks completely, because the concentration of iodine becomes 0 and starch liberates in the conical flask. Its color is colorless, and therefore solution appears colorless. So this is your exact end point. So continue the titration from the same point now, and continue it till you get a colorless solution in the conical flask. See this exactly. So this is your end point, and it is 12.2. Is 12.2. See, I have written in this column that for this particular 10 ml of K2Cr2O7, the end point is 12.20. Okay. So this is your pilot reading, and now you continue the titration in a similar way. So I have already actually performed this experiment in the laboratory in a similar way, and I have got the second reading, that is 12.00. What is the second reading? 12.00, and I have also got the third reading, that is 12.00. And therefore in titration, you have to continue the titration till you get 2 consecutive constant reading. And I have got already these 2 constant consecutive reading, and therefore the end point of the first part, it is 12.0. So in this way, friends, for standardization of Na2H2O3 solution, that we have taken K2Cr2O7 to standardize it, and the end point is 12.0. And now in connection with this, just you try to calculate the normality of Na2H2O3, because this is your aim of this part, that consider this equation N1V1 is equal to N2V2. So this N1V1 is supposed for Na2H2O3, and this N2V2 it is for K2Cr2O7. Okay. So N1 is the normality of Na2H2O3, which is to be calculated. V1 is the volume of Na2H2O3. See, volume of Na2H2O3 means end point, and therefore I have written here value of V1 as 12. Then N2 is the normality of K2Cr2O7, and the normality of K2Cr2O7 is given to you, and it is 0.01 because it is N by 100. See this, N by 100. So N by 100 means 1 upon 100 means 0.01, and the value of V2, that is volume of K2Cr2O7 that is taken for titration is 10 and therefore 10. Value of V2 is 10. And just you calculate this like 0.01 into 10 is divided by 12. You will get N1, and N1 means nothing but the normality of Na2S2O3, and it is N1 is equal to 0.008 normal. So in this way you perform this experiment and calculate the normality of Na2S2O3. Now actual aim in this experiment, our aim is to analyze the water sample with respect to chlorine, because our aim was to determine the chlorine present in the water sample. And for this part now, we have standardized this Na2S2O3 using K2Cr2O7 in the first part, and we have got the normality as 0.008 normal. Now we will perform the second part of the experiment, that is analysis of water sample. Okay, so just you see the demonstration for this. See the demonstration for this now. Just you take again, instead of this K2Cr2O7 now you take the water sample, given water sample containing chlorine. So this is the given water sample containing chlorine. So again you fill your burette with Na2S2O3 solution up to 0. Okay. You fill your burette with Na2S2O3 solution up to 0. Adjust to 0 now. And see, in the second part, instead of K2Cr2O7 now, you take the water sample. What is the procedure? That you take water sample, again 10 ml, with the help of this pipette. You take 10 ml of water sample, again adjust to 0, and transfer it to conical flask. And then you, in the second part of this experiment, you need not to add HCl. See, this reaction takes place at ordinary condition. In the first part of the experiment, the reaction, it is taking place in presence of concentrated HCl, and therefore we have used HCl. But in second part, during analysis of water sample with respect to chlorine, you need not to add this HCl. Directly add now this half test tube of Ki solution. Directly add half test tube Ki solution. And again wait for 1 to 2 minutes for the liberation of iodine. See, this iodine is generated now, and in the second part, I have already explained you the theory part of this experiment, that during this second part, the iodine generated will depend upon the chlorine present in the water sample. Suppose in water sample, the number of chlorine molecules are 10. Then equivalent amount of iodine will be generated, like 10 molecules of iodine will be generated. And therefore indirectly, here we are getting the concentration of iodine, but it is equivalent to chlorine, and therefore we are getting amount of chlorine in the water sample. And this is called as iodometric titration, because there is a generation of iodine. So iodine is generated, and after 2-3 minutes, again you make it faint yellow by titrating against Na2S2O3, and in between then you add a starch solution. In between you add a starch solution, and again continue the titration. See, this is after adding starch solution, you will get again I2 starch complex, and when the concentration of I2 becomes 0, you will get the colorless solution. So you continuously titrate against this Na2S2O3 and take the sharp color change from again blue to colorless. So this is the end point of the second part, and the reading is found to be this 2.5. Reading is 2.5 for this particular 10 ml of water sample. The reading that I have got, it is 2.5 ml of Na2S2O3, and I have repeated this, and for 10 ml of this chlorine, that is water sample, we got 2.3 reading second time, and also third time we got the 2.3 reading. So in this way, you have to continue the titration till you get 2 consecutive constant reading, and I have already got this 2.3, 2 consecutive constant reading, and therefore 2.3, it is the end point of this second part, that is analysis of water sample. And now you go for calculation like this. Again use the same equation, N1 V1 is equal to N2 V2. See, this is water sample containing chlorine, and this is for suppose Na2H2O3. So N1 is the normality of this chlorine. N1 is the normality of chlorine, because our aim is to determine the chlorine concentration. And unless and until you calculate its normality, you cannot calculate the concentration, and therefore first calculate the normality of chlorine. So N1 is to be calculated. V1 is the volume of water sample containing chlorine, and that is 10, because we have taken 10 ml of the water sample. Then N2 is 0.008, because N2 is the normality of Na2H2O3, that is we have already calculated in first part, that is 0.008. And V2, that is volume of Na2H2O3 for this 10 ml of water sample, the end point of the second part is 2.3. So 0.008 into 2.3 divided by this 10, you will get the normality of chlorine present in water sample as N1, and it is found to be 0.0018 normal. 0.0018 normal. So in this way, first you calculate the normality of the chlorine present in the water sample, and then you go for concentration. Concentration of chlorine is equal to normality into equivalent weight. This is the formula for calculation of concentration, that concentration of chlorine is equal to normality of chlorine multiplied by equivalent weight of chlorine. And normality, it is found to be 0.0018, and equivalent weight of chlorine is 35.5. So you will get the answer in grams per liter, because always concentration is calculated in grams per liter. So 0.0018 into 35.5, the answer will be in grams per liter. But friends, suppose we want to calculate it in milligrams per liter, that is in ppm, then you have to multiply it by 1000. So 0.0018 into 35.5 into 1000, we will get the answer in milligrams per liter. Means we have converted grams into milligram, and you know that milligrams per liter is nothing but ppm, because both the units are same. So the final answer is 63.9 milligram per liter or ppm. So this is your final answer, that the amount of chlorine present in the water sample is found to be 63.9 milligram per liter or ppm. In this way, in result, you write that the concentration of free chlorine in the given water sample is found to be 63.9 milligrams per liter or ppm. And I have already told you about the concentration of chlorine present in the drinking water. It should not be greater than 250 ppm, otherwise it will be dangerous for drinking. And it is now 63.9, so it's okay, this water sample is suitable for drinking. Okay, so thank you.